Hey, welcome everybody. This is the last lesson for this COVID semester. We're going to be looking at momentum and impulse in physics, which will be the last bit of information in terms of moving objects, which is dynamics, the forces that are related with them. This one has not to do with diagrams of force necessarily, but a few new formulas and new concepts and ideas. And sometimes when things move, you could start working with the free body diagram, and then after you get the force, the acceleration, you're still, if you need certain information like the momentum and the impulse, you could ask the questions on the free body diagrams about the object's momentum and impulse. So momentum and impulse will be qualities of moving objects. It's not a subject I'm very familiar with in terms of my own education. Momentum itself and impulse are qualities of the free body, and they're also derived in order to find how much energy moving things have. Beyond that, you'll see a few applications that definitely measure momentum. And so let's try and keep this as short as possible, even though it is very complex. When you are done this, you will be able to do the final assignment, which is long. Take your time. Do your best. Let's go. I went through it for the before the class, just to take a quick look. Interesting. Whose line is this for? Take a look at these two objects below. You have a sense that both of these objects would be very difficult to stop. Right? You can hardly stop moving bus and a bullet. It's because they are moving with a lot of momentum. Right? Catch a bus, catch a bullet. You're gonna need that distance and that force to do that. And that's exactly the opposite momentum that you need. So momentum will have to do with those quantities. Let's take a look. All objects that are in motion have momentum. So I noticed there's a few questions, so we're going to take some in. An object's momentum depends on two things, mass and velocity. Momentum is defined as the quantity. Would you please stop doing this? In physics, momentum is defined as the quantity of motion of a moving body. This is the definition. As you can see from its formula, momentum is the product of the object's mass and its velocity. And we use the letter rho in physics, which is a P, an older version of P, call it rho, but I can call it P for now. Literally mass times velocity. So let's put some words here. Momentum. Oof. Oof. Plug my mass. This is one of the formulas that we will require going forward. It is expressed, if you look at the units are going to be a little odd too. So the units are kilogram times meter, divided by seconds. So the units are kilogram mass, the kilogram meter per second. What I do is I always put a little bracket here and write it down, but we might fix that. Kilogram meter per second. Get kilogram meters per second. Now this is where the units get a little confusing in physics. This is not kilogram per meter, right? You can say, oh, per meter, and maybe I'm going to add kilos. This is not what's going on at all. It's kilograms per seconds, meters per seconds, but it's kilogram meters. Hard to explain. So if you have, visually it's really hard. 1 kilogram and 1 meter. You divide that by 1 second. So basically what this is, so it's visually it's kind of difficult, but mathematically we can express it. If we increase, so imagine that we always want 1 to be the answer of this formula. So this is the same formula right here. If we have 1 kilograms times 1 meter per second, then you would get 1 times 1 divided by 1 second equals 1. If you increase the kilogram to 2, you want to keep 1 as the momentum. So you have a different object that is more massive, then you would have to reduce the speed. Let's remove this one. This is 1 meter per second. So you would have to reduce the speed. So what this is saying is the momentum that you get is a quality of the moving mass. So if the mass is 1 and the mass is 1 or 2, you multiply that with the speed, 1, 2, 3, you get a quality here, because that number is reflected, 3, 4, 5. Momentum would be a quality of the moving mass. Can I write this here? Oh. Hold on a second. So the momentum would be a quality of the moving mass. Literally moving, not accelerating. This is not an acceleration that we talked about. It's velocity. So the velocity, the moving is the v and the mass. The momentum is a quality of the moving mass because it's a little difficult to see in the real world what kilogram times meter divided by second is. Okay. It's odd how, dollar per second makes a lot of sense. Dollar per minute. Dude. Meter per second. Kilogram per second. Newton per meters. You get an idea of what it looks like, sounds like. But when we talk about kilogram meters or kilogram seconds or meter seconds, we're like, what is that? It exists. Harder to see. And maybe that's why we kind of dropped some of that when I was younger, because it's more of a quality. Quantifiable quality. I want to take more notes because there's a little thing. Looking at this formula, you can see why speeding bullet, slow-moving bus, despite their different masses and velocities, both have a lot of momentum. So the bullet has a small mass, great velocity, so immense momentum. And the bus has great mass, but slow velocity. It's still incredible momentum because the mass is so big. So basically, even you as a person, by going at a certain speed, will have such momentum that it will be dangerous, difficult to stop you without great energy involved. Momentum is a vector quantity because the velocity is a vector, so the momentum is a vector. Let's so much better when it's plugged in. You can see why a speeding bullet. There are two types of momentum, linear and angular. This one is linear. You may use the units shown below. Hold up. So a few questions. The object is at rest. There is no momentum, right? So v, when v is 0, no momentum. Momentum is the product of an object's, what does it say here? Mass and velocity. Momentum is measured by kilogram meter per second. Momentum is a vector or scalar? Vector. It has a direction. Remember, vector has an arrow, which is a direction. Momentum acts as the of direction, the same direction. Because if it was not the same, we would have put a minus. Goodness, we would have put a minus in front of this. It's the opposite direction. Next. Calculating momentum. Okay, you get the idea. We're gonna go pretty fast here. So 1002 times 15. So let's do a quick example because we want to write. So momentum is P. P is unknown. M is the mass for 1,200 kilograms. Running, so the velocity of the rhinoceros is 15 meters per second. So we will find the vector. You don't need to do this. Meter times velocity. And so 1002 times 15. So 1 times 15 will be 1500, and then 2 times 15 for the 200 will be 3000. So we're looking at 15,000, 3,000, 18,000. Right? Kilogram meter per second. Kilogram meter per second. 0.8 is 10 to the 4 kilogram meter per second. Lots of units. A frog left a lily pad with a speed. What is the frog's momentum? So again, we're not talking about the acceleration of the frog. At a certain point, its speed is 1.2. At that point, it has momentum of a certain value. Before that, it hasn't reached that speed yet, so it does not have that momentum. But as he reaches that speed and has that momentum, things will happen. Okay. You can stop the video and try it if you want. I think you get the idea. Change in momentum. Let's just see if there's one more complicated problem. This one. All of these have my mass and my velocity, right? Mass, velocity, velocity. This is a question in reverse. What's the mass? But give me the momentum. Kilogram momentum, what's the velocity, right? So these are easy. Giraffe has a momentum and a velocity. The weight. Oh ho ho, the weight. Let's do number 5. Real quick. A giraffe has a momentum of 1.3 times 10 to the 4 kilogram meter per second. Don't hesitate. Write it down. Write the units down. A velocity of 13.4 meter per second. What is the weight? What's the weight again? It's the force, Fg. To mg, which means I need my mass. So in order to find my mass, say rho is mv, momentum is mv, m. So what do we do to get just m? We divide by v, m would be rho over v. M can be found with 13,000, sorry, divided by 13.4, give us 0.9. Kidding. 13,123 divided by 13.4 is 9.7. 970.5 kilograms. What I was looking to do was take this, divide that by 13.4, and get not 0.9715, but because you can see how super close it is. If it would be divided by this, it would be 0.97. That it's 0.0715 kilogram. Or if we put this scientific notation, times 10 to the minus 2. Things wrong. Times 10 to the 2. Previous answer is off. Not that off. Missing my times 10 to the 4, which is up here. And if you go back 1, 2, you go back and 2. Here. Kilogram. Okay, is that the question? No, that's not the question. We want weight, is Fg, is mg, is 9 point. I'd rather work with 970.15 times 1 times 9.81. I don't put the minus again. I do that in my head. Right here. 9517.16. I'm happy with that. That way of writing, by the way. And one more problem, the last one, just to check it out. We got mass, we got velocity, so we can have momentum, right? It strikes a 250 kilogram bear charging northwards at 3 meters per second. So this bullet was shot southward. Find the momentum of the bullet and the bear. Okay, just the momentum of the bullet and the bear. So this times this will be 7, right? 1% of 700 is 7. and then 250 times 3 will be 750. Sorry, I have a headache. Right, so 7 instead of 700 and 750 north is the direction of the vector. No problem. Let's get into the real deal. So, when we talk about an object that has a constant velocity, we can determine that it has a momentum, which is a quality of the moving object. What happens if the velocity changes? You know, if I say, so this person had a velocity of 7 meters per second, and then it had a velocity of 13. And I could then ask you, what was the momentum before? And what was the momentum after? So imagine we take a mass. Put this here, and then I'm going to put the information above. I'm going to try this one more time with my face. Kilogram 3. Velocity would be 8 meters per second, and during the second, this is a difference in time. On the second situation, momentum, that's not the right letter for momentum. Oh, this row 1 and row 2. The mass would be the same at 3 kilograms, but this time the velocity would be 12 kilograms. So we could ask, what's the velocity here, the momentum here, and then the momentum here, which is mv1 and then mv2. This would be 3 times 8, and this would be 3 times 12. So all I'm doing is a quick example for you. Momentum 1 is 18 kilogram meter per second. Momentum 2 is 3 times 12, 36 kilogram meter per second. Confused. This is a 24. I blame my headache. 24. So we could then ask, by how much did the momentum change, which would be called delta P. The change in momentum. Delta P is P2 minus P1. The same way that delta T is P2 minus T1, or delta V would be V2 minus V1. We're asking, by how much did this number change from this number? Or, yeah, how much, what's the difference? So that's why we use a difference. And we use a difference from the past, the one. So we could say that change in momentum was 36 minus 24, and the change in momentum 12. Kilogram, same units, meter per second. This is what we have with our equation up there. We're saying that you can change the object's momentum by changing its mass or its velocity. Mostly its velocity will change its momentum. Therefore, the formula is finding an object's change mass as this. So if you change, so is there a formula for this? Let's create the formula. We take the original formula with these two vectors, and we state, because we can clearly see here a correlation, I've increased 8 to 12, and my momentum increased from 24 to 36. Both of these numbers are directly proportional to each other. And so this is part of the reason why we are able to write the formula as such. The difference in momentum is directly proportional to the difference in velocity. If the difference in velocity increase, the difference in potential increase by the same amount. Well, so that's another important formula, because in your formulas you might find this, and then you'll have to get back here and take this. But basically, when you're looking at this, you are looking at this here. And let me actually add a line for you. Delta P here, P2 and P1 are mv2 minus, from here, m1. This line is what this means. The change in velocity from v2 to v1 can be written this way. The same way that you can group m in front of v2 minus v1, right? You can do that here. That's what this is saying. This is saying that p2 minus p1 is equal to m v2 minus v, right? So this is an insight. Call this an insight into the formula. But we're asking for the change in momentum, then we're asking for the change in momentum. If we're asking to find P2, then we have to give you P1. But you could reuse that formula instead. Right, so if you're looking for actual P2 when you have P1, you can find that. But most questions will ask you to find the change in momentum. mv2 minus mv1. If you have the initial velocity of the object and the final velocity of the object, initial and final. So yeah, so again, I give you two information, v1 and v2. From these two information, you could calculate the difference in momentum. So we did all this. Now we're going to use one formula. Difference in momentum is 3. Mass 1. But because again, we want to know the change in momentum. 3, 12 minus 8. The change 3 times 4. Change 12. 12 what? Kilogram meter per second. We're going to take all this, bring that down. As example. Net force. What does the net force have to do with this? There's no force. There's a mass. But there's no acceleration. But the difference in velocity, like they say here, I won't paraphrase, I'll just read it. If the object's velocity changes, therefore there must be an acceleration. As well, in order to accelerate an object, there must be a net force. Right, so they're saying that inside this idea is the idea of acceleration. we will develop this. Therefore, when a net force is applied on an object, its momentum changes. You apply a force, you apply acceleration, you change the speed, you change the momentum. Let me just write what I just said. If this is 0, you do not create an acceleration. But you increase, I don't know where to put this plus, but I'll put it here. If you increase the force, given that it's the same mass, though, this thing is static, right? It doesn't change. You increase the force, you increase the acceleration. You increase the acceleration. You increase the velocity. What did I say? You increase the force. You increase the acceleration, which increases the velocity. If you increase the velocity, then you increase the momentum. This is from P. If you increase the momentum, then you increase the difference in momentum. This is from this, P2 minus P1. Oops. Right. So again, P1 is a definite value that is due to V1. By creating a force, you accelerated the object, you created a second velocity because of that, which created a second momentum. And then if you say you have a second momentum that is greater, then you've increased the difference between the second momentum and the first momentum. So the difference in momentum increases. This is the relationality. Relationality. Relationability. Relationality. Relationability. That's a little different. Relationality. This is the relation between the things. You get it. Move on, Chuck. You can watch video. Impulse. Let's get into it. Impulse is used to describe an object's change in momentum. Let's go. The impulse is the change in that. What is that change? Change in momentum. This, right? Interesting. The impulse can be calculated by multiplying the force applied to an object by the time over which the force is applied. There's like two definitions for impulse. That's interesting, and we'll look into it. Take that too. Okay, so hold on. So this is a definition, yet this is a calculation. They're not doing the same. Impulse can be calculated multiplying the force, F, applied to an object by the time over which the force is applied. So the difference in time. Why don't we just say T? Some formulas say T. They say J equals Ft. Right? But we will learn with delta T today. So basically, let's think about that for And please take note of this equation. Delta t is simply the time. F is force applied, or force. I mean, the force is always applied. And then J is impulse. We're gonna get into that big time. What are the units? What's going on? So imagine I have this block. You remember last lessons? I got a guy here who had pushed the block, right? He applied a force. And when I press the button on the other lessons, he applied the force for a certain time. And when I let go of the button, the thing was flying at constant. Basically, the moment, this is a moment, right? The time, moment that he was doing this, is the impulse. When we say, oh, I had the impulse to do that, was it a strong impulse or a small impulse? And you can see how the impulse has to do with the time it took for something or for you to accelerate or to block. So many things I want to say. It does not have its own unique units. It has a Newton second. So units, Newton second. They're the units. They're not Newton per second, because that we know what it is. Certain amount of Newton every second. That kind of makes sense. That's not at all what's going on here. Not at all. It's Newton seconds. So again, if we have, for example, an impulse, so imagine you accelerate your bike. Oh, I'm so sorry. You can't see. Hey. Feel bad. So you have a bike and you accelerate it. It has to do with how much force you're going to put on those pedals and for how long to know what your impulse is. If you put 10 newtons on the pedal for 2 seconds, quick example. So, but again, we will do like a 2 situations. So imagine we have we're just trying it. So 2 Newton for a time of 3 seconds. Then the impulse would be 2 times 3 Newton times seconds. So you end up with 6 Newton seconds. Okay, imagine that you kind of want the same impulse, but you want to take a little more time. Okay, so you're going to increase this to 6 seconds. If you increase this to 6 seconds, yet you want the same impulse, you're going to have to reduce this to 1 Newton. Because 1 times 6 will be 6. And so you can see how it's the same impulse if we get a competitive biker versus a bike. Okay. So we get a competitive roller. What is it called? So he wants to put a force of 2 Newton when he accelerates. He wants to put 1 Newton. He's willing to do it for 6 seconds. He's willing to do it for 3 seconds. He's going to be going at a certain speed, and so will he. They might end up at the same speed. We're not sure yet, but clearly this one will be in front. Okay, for a certain time, possibly. So what is the impulse? So the impulse, again, has to do with the object itself. Right? Because we're applying the force on the object. So it's a quality, again, of that object. It has to do with not only accelerating, because we can clearly see that's an acceleration. There's accelerating going on, there's force, but it also has to do with deceleration. Deceleration. I just wrote it. But it's a quality of the object to which we change its velocity by applying a force. Okay, let's go back. Doing good. Newton's second law. Formula for impulse and change are another way of starting Newton's second law. Start the formula with F equals ma, you get A multiplied both sides. What they're saying is unite those two definitions. Let's unite those two definitions. So if impulse is used to describe a change in motion, which we are not quite sure how yet, let's take the original formula here, from which we can calculate impulse, and derive it, especially using F equals ma instead of F. What happens when we put ma there? J equals, you just vector, a vector. J equals F, ft or delta t. J equals ma delta t. Now the book says, what's A again? So A from the original description is Vf minus Vi, and we say V2 minus V1. Is this okay? Time. So J. So let's take all of this now. Put that inside the formula instead. M. And I'm not sure if that's what they want me to do, but I know like what I want to do with it. Delta t. Now, the question is delta t here the same as t here? Let's think about the idea. The person went from velocity 1 to velocity 2. It took them a certain time to do that. In that time, we had t1 and t2, which was the start and the end of our scenario. Let me do my better drawing. Start, end of our scenario. At which point we had a v1, a v2, and that's what we find acceleration with. So t1 minus t2 means t, the time it took. So yes, in this case, and most case, delta t is also t. We just never write it because we write t so often. So it is the same thing. If I say the experiment took 20 seconds, time of 20 seconds, then this is 20, this is 0, and 20 minus 0 is 20. Is 20 supposed to be here? And is 20 supposed to be here? Yes. Because it took 20 seconds to change its speed using that force. You can see how it's the same now. Lot of stuff. M is the same, it can be cancelled, it should be cancelled. We get J is V2 minus V1. Get my point? Well, what is that? That friends, is the difference in momentum, isn't it? So J is the difference. What did they write here? Okay, they went a step further and expanded J with its definition. So this is true. But let's expand J again. J is this. So F delta T. F delta T. The reason why they do that is because you have things that you recognize. J is kind of a new thing in our problems. F, E, these are all things we can measure in an experiment. Delta P is M delta V. So you have M and you have the differences. This is T2 minus T1. You normally get T. This is V2 minus V1, which you get both. So again, if you have T, V2, V1, M, F, you can talk about the object using that formula now. So we've taken things that, let's go back here. So we've taken interesting characteristics of objects and mashed them together in order to find which different characteristic of objects that were true, to then put them together and find a formula that we can use with our more basic elements or our drawings and our diagram. This here. So we're going to use that formula. We should be writing that formula down. F delta E M delta V. Read quick. They said impulse equals change in motion. Okay, so physically, if that's the case, then the impulse is the change in momentum. So your momentum at V1 was a certain number, and then you kind of accelerated, you went faster, you pushed, you forced, and that's your impulse. And the time you took to do that, that moment between your V1 and your V2, that's your impulse. That's the quality of it. After you hit V2, you don't need an impulse anymore, right? The impulse is within that moment between the V1 and the V2. We can look back here for a second. The moment is delta T, right? That's a moment. And within that moment, you had a change in velocity, V2 and V1. Makes sense, right? Within that moment, there was a force on the mass which changed its velocity. Okay, impulse is the product of, don't need to read, you can say force and time, no? Force applied in the time over which the impulse is measured in Newton seconds. Impulse is a vector. Impulse acts in the object's same direction. There's no minus for this. Same direction. See that vector? Same direction as that vector. Impulse is equal to an object's momentum. Wait, what is it? Impulse is equal to a change in momentum. The famous egg drop activity. You all know about it. Drop an egg, save the egg. We have a virtual way of trying this. You click here. I welcome you to try it. Click it in a second. But let's talk about the issue. The egg accelerates from the roof to the floor. This is not the problem that we're having. The real problem that we're having is on the floor. So let's go into a very like macro view of the egg. So the V1 here is 0, the V2 here is like 60 meters per second minus 60 meters per second. The real problem is here when the egg touches the floor. His V1 is 60 meters per second minus 60 meters per second. His V2 is 0 meters per second. The question is, how much time did that take? And if we could increase that by even a little bit, then we would increase the difference in momentum. M delta T kilogram. And you can see here how that matters. Let's take the formula here first. Take this formula. You change this around and you keep playing with your formulas and FT and all that, you end up with our formula we had. Let's take it again. F delta T equals M V. Delta V is up there. You can see V1 and V2. The mass does not change. Delta T is the time it took for the egg to change velocity from this to this, which means also the force that it experienced in order to do so. Let's look at this side of the problem first. So a problem like this tells us that if we know the mass of the egg, do we know the mass of the egg? How much does an egg weigh? 20 ounce. Large header. And it will convert ounce to gram. 7.2. Oh, if you want to do it manually, 722.9 0.7. So imagine a mass of, let's just say 0.5 gram, because this is a big egg. I want smaller egg, and I want easy numbers. It's an example. 0.5. Delta V was a difference in V. So V is V2 minus V1. In this case, V2 is 0 minus 60. We have a plus 60 for delta V, so plus 60. So this side has nothing to do with the experiment and our attempt to save an egg. This side has to do with an egg, and the velocity that it attained is due to the height and the mass of the egg. Like, these things you can't work with, right? We always start here. Every student has to drop the egg. You know, we're all here. Hello. I'm not naming you because it's on YouTube. You get my point. So this side has to stay 30 kilogram meter per second square, and that's and you'll notice that we probably want to give you the same kind of. So if this side has nothing to do with saving the egg, because what can you do? The speed has to be this when you drop it from that height. the mass has to be the same because we're trying to give you the same egg. So if this side has to stay the same, that means you need to work on this side. By increasing the time, you would lower the force, right? Because this side has to be equal to 30. So if you have a force of 15 and a time of 2 seconds, and multiply that, that gives you 30. So if you could take 2 seconds to drop for the egg to reach its impact, like literally it's impacting and it takes 2 seconds to slow down, the force is only 15 Newton, which seems tremendous for the poor egg. But if the egg hits the floor faster, or there's nothing to bounce the egg on, then the time would be smaller, and 0.5 times what equals 30 times what times 60. So you can see how we keep increasing the force if we keep lowering the time. So in other words, if the egg falls with no protection, it experiences a lot more force. But if the egg could be cushioned and it would press on the cushion to a certain distance for a certain time, then we could increase this number, which could be something like 0.1 all the way to 0.2 seconds. But that would be a 2 times factor, which would divide this part by 2 times. So even if this is a very small number, if you change it by just a fraction, that ratio is respected when it comes to calculating the force necessary, right? So let's do more examples. So if it took 0.0, that would be really fast. 0.05 seconds. It makes a lot of sense for an egg that would crack. No? So 0.05 times what equals 30? So 30 divided by 0.05. $600. So that's 600 Newton. Imagine that you instead of having it do that sound, it would do no sound because it's going slow. That it might take 0.3, maybe 0.3 seconds. 0.3 seconds is not very long, but if there's an actual cushion there, it would save it. So 0.3 times what is 30? 100. So 100 Newton will be a lot less. 100 Newton, yeah, will be a lot less than 600 Newton. And one might ask, how in the world will this egg sustain 100 newtons of force? And it has to do with the time in which you apply it, right? If you apply 100 Newton very fast and then you stop, have you cracked the egg? Cracking an egg is going through the egg. So if you don't have time to go through that distance, why would it crack? Why would it crack? It's the same thing. You take the egg on the side like this, you apply 100 Newton, you stop, might not crack. Not something I'm familiar with, again, so I've never done this experiment myself, but you can see a little more of what's happening. Here, you click here, open this up. A small egg, drop 1 meter, I know you can't see. Landing surface, hard floor. So hard floor, 5 meter. Let me just. All right. So big drop. Drop the egg. It's dropping from 5 meter. So this can give us the speed of the egg, 5 to 1, and the result. Also some information. 132 newtons. Because of the time it took. This is very hard to calculate, right? You need a really good equipment to find. That's why we're given to work with. Change the condition. This time we will give it 1-inch foam. Remember the time it was 0.003, I think? Saved. The time here now is 0.03, not 003, which is 10 times bigger. Force applied within that time can be found here, 13.2 Newton. So the mass did not change, the velocity did not change, but the time did change, saving the egg. Look at the size of the egg here, 40 grams. 40 grams? I think that's what I had. My problem was a little higher than that. It's 400 grams. Mine was 400 grams. Why did I put 400? 500 grams for an egg? Oh my goodness. Wait, what? Oh, okay. Well, I'm right, and this program is wrong. Kidding. Let's go back. Yeah, why would the egg size be 40 gram? The internet told me the egg is 10 times that. Things you can't change. Send them an email and they can have you calculate some information. So basically the formula we saw was taking this. F was alone delta V, difference in velocity over the difference in time. So by calculating the real force applied on the egg, this formula, you will be able to tell at which point the egg is safe. I don't know if the force to break an egg, but a certain force would be enough from what I see with an egg. Moving on. Momentum, impulse, and car crashes. I don't want to play those too much. It's a great video. You should look into it. How much time the car brakes, is the safety, the belt also stops your momentum, protecting you. There's a lot of momentum with this maneuver from the plane, which turning, etc. This is good.
And let's also assume the car's front end crushes 1 foot with uniform.
So the distance that a car can crush If it can only crush 2 meters, it will take a certain time to do so. If it can crush 5 meters, it will take a certain time to do so. These are values that matter in the impulse and the transfer of energy. To you, to me, to everybody.
Uniform deceleration of the passenger compartment throughout the crash. In
This car brakes, crushes a little bit.
However, if the
Driver took the impact, and then if this one crushes more time,
the deceleration would be cut in
and as you can see, the change for the driver is less. Whereas this one here had to adapt to the car. This one took more time to adapt to the car.
impact is the base and
Same reason why these blow up when they hit.
film. The crash because his
The way that it blows up is to protect the driver in
This driver decelerated in a small fraction of a second.
oof,
Experienced
yeah.
forces that are
So the deceleration here was very small. So by looking at an impact, that's how people have a feel for it. They're looking at it and they're like, oh my goodness, that was crazy, that was too much, etc. And then they rush to the scene because they feel it.
over 200 Newton and his buddy collisions
Like Newton, this is impulse also.
theorize that the total quantity of motion, which he called momentum, doesn't change. It's
The reason why it works is because those balls are made of a metal that does not crush. If it does not crush, the energy is transferred and the momentum is kept.
momenta cancel each other.
Here we have more examples of momentum.
Inside the passenger compartment of each car, the occupants would experience the same deceleration
And I can't believe physics is not part of the curriculum mandated for everyone, because this is a very important lesson.
as a single vehicle crash into a rigid barrier.
Right. So they were just saying it was the same crash.
The dy-
You can see how it reacts the same way.
as a single vehicle crash into a rigid barrier.
Yeah, so basically if you hit another object, if you both go at the same speed, which is what's happening, it's the same as hitting a wall. Yeah. If this car has less mass, then your mass is stronger, and this car will start going in reverse. You'll kill that person. So that's why if you hit a bike with a car, if you hit a smaller object with a car, it's very dangerous for the other object because it's less massive. If you hit a big truck that has like immense mass, the truck has a good chance to continue its motion. You're going in reverse. You went from 60 plus 60 to minus 20. This is even more change in velocity, right? Like if you start going backwards, you can't tell me this is not worse than this. Because this went from 60 to 0. If you start going backward with your car, it's from 60 to minus 20, difference of 80. Right? And that's why collisions with trucks are more deadly for the driver of the car. Because it goes in the other side, another sense. Excuse me.
Implications for the occupants of both the heavy. The more massive car would drive the passenger
This is an impact from the
backward,
corner of the cars.
causing a greater speed change in the lighter car than the heavier car. These different speed changes occurred during the same time.
My goodness, is that dangerous.
The lighter car would experience much higher
You
acceleration,
can see
hence
the,
much higher force.
the change in momentum in 2 directions. This is basically a 2D momentum
Lighter, smaller cars,
information.
car crashes. Weight is
This is grade 12 momentum information. You're going on the y-axis and the x-axis. We just need, we don't even look at that for 11. Newton. Ending in such a positive note. Why? Calculating the impulse of a 50 kilogram a man experiences when he lands on firm ground after jumping a height of 4 meters. That's a great problem. very little information, and we're going to get all the physics out of it. You can pause me to do it. Feed me. Calculate the impulse of a man. 50 kilograms. The distance will be 4 meters. This is a great problem. He lands on firm ground, which means not much. Because we don't have the land in numbers. What do we want? Impulse. Calculate the impulse. J. Known. So this is my favorite stuff. Start with J. J is what? Go back up and look it up. J is the difference Ft, but it's also mv. Yeah, and it's also delta P. So J will be delta P. We could also say at this point that it's equal to all those other things. So Ft, F delta T is also equal to M delta V, right? Because this is equal to this. And the this part is where I take this part. And this is the original formula. Okay. So basically what we have here is infinite possibilities. If you have the mass and the velocity, you can find your J. If you have your T and your F, you can find your J. Like, don't need all of it. You just need like 2 of them and you find your J. So what can we take? What can we have? So the distance 4 meters, what does that tell us? By the way, we have the math. So the distance is 4 meters. So you've seen from the previous modules that if your distance 4 meters, your acceleration is g, 9.81 meters per second square. V1 was 0 because he jumped from a height of 4. So they're trying to say that it's V2 is unknown. Excuse me, I have a headache. You're not gonna believe me. True. I want to slow down a little bit. I'm having a lot of fun. Can you find me an equation that has V1, D, A, in order to find not the time that it took for the man to fall? What do we want from this? We want his velocity 2. Isn't that what we want? V2? Right? The velocity at which, like, at what speed was this man going after he jumped? That's what we want, right? So we'll find V. So why do they want to find Vf? Okay, so basically they're saying that now on the floor, like the egg, the man's foot, V1 is what I'm trying to route, because V2 is, so this is going to be the impulse problem. Impulse problems are always going to be on the floor. We took that information from V2, brought that as a V1. That's what they're looking after here. Yeah, so VF, no. So you telling me you don't need this? So, it's okay. So looks like we're working here with our problem. We're mixing up these two things, but I want to focus on this here. This is where we are. Take these formulas, which we did. We have this information. We find the initial velocity there. Okay. Don't have them handy with me. Continue. So, Newton 5 acceleration. Dynamic kinematics. I could just check they're like right there. Oh my goodness. Yeah, VF square is VI plus 2 times the distance. VF is VI. VF2 equals VI2. And here they said VI2. Make my life better. So let's teach those nerds. So V2 square is V1 square plus 2AD. V2 square plus, we'll put a minus for the 4 meters, 2 times minus 9.8. So V2 is going to be the root of, notice the square is gone, okay? And the minus cancel out. Perfect. 9.81. 3924. And the root, please. 4. 6. 6. This answer is plus or minus. Remember, this is a root. Both of these numbers timed by itself will be 39. So is it going to be a plus or minus? The 2 is a minus going down. Oh, 2AD, Chuck. Is 1. I forgot the 2 times. Let's do it again. And just time 2 here. 2 times 8. Root of 7848. Point 6. Hard to see. 6. And it's a minus. If you would not have seen it at this spot, you would have seen it at another spot. Sure. Because the problem would have broken down. The numbers would not make sense. We did notice it early. Note. So basically, okay, so we have V2. What do we do with V2? we can find delta V. Do we have the mass? 50. It's over already. So J is equal to M delta V from all of this. J is delta P is delta V. And J times V2 minus V1, which is delta V. The mass is 50. And now the speed is minus 4, 6. Minus, what's V1 again? Oh, hold up, am I confusing? Yeah, I'm confusing things. V2 is 0, V1 is the point. V2, 0, minus, V1 is minus point, plus, and your impulse is positive, upward, which means your force pushing against him is also upward. What's 50 times that number? By 10. Sure. So just timed by 5. 442. Units, please. God. So if you don't remember the units, and I don't blame you, you look here. Kilograms per, kilograms meter per second. Kilograms meter per second. Or Newton second. Because this is Newton second. And the impulse itself always measured in Newton. Huh. Is this equal to that? Let's just make a quick check. Kilograms meter per second, is that equal to Newton? What's a Newton? It's a mass times an acceleration. A mass is in kilograms, an acceleration per second square, and then it's multiplied by a second. This is Newton timed. You time S, you get one of those out. Kilogram meter per second. The same here. Meter. Nice. Yeah, the units are good. Could have checked earlier. So let's just write Newton second. Maybe. On sync. Okay. This number does not really tell how hard the man hit the ground. Right, because we don't really have information about the firm ground. We can qualify the ground, but we can't quantify the ground. In order to quantify the ground, we would have needed the time that it took, or the distance that he would have traveled in the ground or in the surface, through the surface, to determine that time. And from that time, we would have said, oh, that's a firm ground, or that's a very bouncy ground. That's the opposite of firm. Firm, soft, very soft ground, very yielding ground, soft ground. more problems that you should practice, of course. I know you're a little tired, so we're just gonna skip that. But clearly you can use all kinds of equations. This is an equation you can use. This is an equation you might have to use. I want to show you a little more. Take, I don't know, this problem. We have a mass. I just want to show you what you could do here. So you would write your units. You have a mass. And the velocity is changed from, who cares? And you have two velocities, and in 68 seconds, so you have a time, by a constant applied force is known. What is the change in momentum? So your question A is P equals what? Actually, delta P equals what? Change in momentum. And then you have, what is the magnitude of the force? So this question is B. Question A is delta P. So how would you commence? Need something with this. Let's take a quick look at the, we have M, we have delta V. Because from this here, you can have delta V. You can just build delta V in your formula. This. And we have a T. And we're hoping to have an F. But don't worry, it's all there. So delta P using MVT. Okay, go back in your formula. Delta P using MVT. Not exactly this one. Delta P using MV. And then T after that to find the force. So we could use delta V equals original concept. I was just looking for something more complicated, but we could use this. Get delta P. F would be, because you literally over, and F would be delta P. What is it? F is, right, you could say this, which is the formula that we here, or you can say this. Delta P is F delta T. And so F is delta P over delta T. You have the time, you have delta T is T. And delta P was found. Put it here. Those two things. I love physics. So simple. Think about this. Okay, quick information here. We learn about momentum and impulse, explain words. Why is it more effective to use a steel hammer than a rubber mallet to drive a nail into a board? The nail, the board, hammer. Where do you think I'm from? You drive the nail in there. You nail the board. Yeah. So this is the problem. So what happens when you nail the board? You drive the hammer onto the nail, this, with the impact. I'll try to use words. the momentum of the hammer row impacts on the nail and offers an impulse to the nail. That impulse has to do with the time the time it takes for the hammer to hit and provide the impulse is what matters. This is the difference between steel and rubber. Right? Isn't that exactly the variable that we're looking at? Because again, the same idea is if you go through fluff, you go through a certain distance, which also takes a certain time. Interesting how these two are constantly linked in the concept of impulse. And that's what's going on. Because he's trying to transfer the energy, it takes more time. That energy transferred has to equate into the force, right? And then the force used to push the nail. The nail does not care, but the board cares. The board can only take so much force before it breaks, and the board breaks. This is what breaks. The board. The wood breaks. And we talked about hour 30 minutes again. Momentum and impulse on everyday life. Give me a break. We've done this. Challenge. Done. Just, do we do the challenge? It's an hour. I'm done. I hope that you've enjoyed the semester. I encourage you to take a look at other modules and read on other modules. Oh, hold on. Dynamics. You have to do the assignment. Don't screw this up. Do the assignment. I'll review it. Here. 2-page, do the assignment, then you can scan it. And yes, I do recommend you look into the work and the energy. Just browse through it if you're interested in work and energy, which are not really real things, but they do affect real things. And then if you're really nerdy, like I am, you look into the waves. Because so many things in lives are waves, including electrons. And so if matter is wave, then you're up a different alley here. This is the physics alley. And no other project or anything. Okay, thank you guys.